Alright, well I can see you're just about ready for some more fun. So this is the fifth of about 7 videos on lectures about potentials and fields. We're going to switch gears now. The past 3 videos have been mainly taking some potential diagrams or something and turn them into fields. Now we'd like to talk about some of the other interesting things that happen with potentials. We want to talk about that other part of the potential, which is how it relates not to the electric field and therefore to forces, but to potential energies and to work and to kinetic energy and all that other fun stuff that you all remember from Physics 1 and you loved so much. Alright, so let's go on. You know, I always like to start with a question. Here's the question. So I've got this map. So now I've got a two-dimensional map of potentials. We were just looking at a one-dimensional equipotential map. This is a two-dimensional one. So that each point along one of these lines, say this 0-volt line, has the same potential, right? It's 0 volts. Here it's 10 volts, here it's 20 volts, here's 30 volts. At a couple of these points, I've labeled exactly what that potential is. 35 volts way up here, minus 15 volts way down there. So you can sort of think about what that means a little bit and try to figure out which of these 5 points, A, B, C, D, or E. So A, B, C are down here, D is up here a little bit, and then E is out in the corner. You want to figure out which one of these would be a good place for a negatively charged ball to be stable. All right. So if you pause this, think about it a little bit, write down your answer, write down your reasoning, and then possibly even start talking to a friend after you've written down your own reasoning. Talk to a friend. If he convinces you otherwise, if he changes your mind, write down your new answer, then write down your reasoning again, and then go on and listen to what I think about it rather than what you think about it. And if we differ, then try to figure out more or less why we differ and how you can improve your thinking about things like this in the future. All right. So go ahead and pause. And then we'll be ready for this whole thing, right? It'll be great. You'll love it. Okay, so I've got all these points here. Now, how am I going to figure this out, right? Last time we were just looking at the sort of slopes of uniform fields. Now this is all weird and stuff like that. So how are we going to do this? Well, remember last time in Lecture 1, I did some stuff with some point particles and said this is where it's stable and where it's not stable. We're going to look at the same thing there. We're going to look at a graph, all right? But how am I going to look at a graph here? I've got two-dimensional things here. This is actually a plot of the potential, but I can take a cut of this two-dimensional map and turn it into a real plot, into a regular plot rather than a two-dimensional map. And how I'm going to do that is I'm going to make a slice right through A, B, and C. Right, I'm going to make that slice and then plot what the potential is along that slice. So you see at A, we've got 0 as our potential, 0 volts is our potential at A. We come way up here for B. These things aren't supposed to move, but they do anyway. Ha ha. So we come down here come up here to B, and we get this big peak, and then it falls down 30, 20, 10, 0 to the negative region, down to minus 15, way down here at minus 15, and then it starts going back up. So this is what I've got for that line. What does the potential look along that line? All right. And you can see that I've marked these places well, A, B, and C. Now we remember this thing over here, that the potential is equal to Q times V at some X, right? So we can use this potential to tell us what the potential energy would be if we put our object wherever. So eventually we want to get to the negatively charged ball, but it's easiest to just start with the positively charged ball, right? If we looked at a positively charged ball, then the two graphs look exactly the same. The only difference is going to be the scaling factor out here, right? So this will be in volts, V is in volts, U is in joules. Okay, well, what are we doing with these joules? We're not doing anything with the joules right now, and I don't really care about the numbers. We care about the peaks and valleys and things like that. And what do these peaks and valleys mean as far as motion and stability and things like that in a potential energy diagram? Well, you've seen this before. You've seen it over and over. What does this stability stuff mean with this potential energy diagram? Well, means basically this: everything wants to move downwards. It's just like if you're pouring water into this thing, the water wants to get down to the bottom. If I dropped a ball right here, right, and this was the profile of a bunch of dirt, right? If I built up some mounds of dirt, and this was a profile, if I dropped a ball here, it would fall down here. If I poured water, it would all flow down here and then sort of bunch up at the bottom. So that's exactly what we're doing right now, is we're looking for where would the water flow. Wherever the water would flow, that's a stable point. The place where the water wants to go, that's where it's stable. Where it's not stable is everywhere else. And C, for the positively charged balls, C is where it would want to go. Positive charge is going to want to go to this smallest value here, this negative value. The negative isn't important, but the fact that it's the smallest possible value in that region is important, right? Anything that we put between here and here, right? Anything from between B and a little bit after C, we don't have anything after there. We'll all try to get to C if it possibly can. If it has any way it can, it'll try to get there. So that's what the stability looks like. A is not stable. Anything on this other side of B is going to keep on going to the left and forever, because I know what the equation is that I used to make this. It'll go on forever. But it will go on, but if we don't know what the equation is, it'll go on until it gets to a little pothole or something like that, just like this area C is. So what about when we make this negative? What's going to happen? Well, when it's negative, we're going to multiply all this stuff by -1, right? So basically, we're going to flip this graph over, right? So I'm going to flip the graph over, and we get this deal here, right? Now that's flipped over. What does that mean? That means the stability is changed. So now the lowest point, the point where everything wants to flow to, is going to be this B point, right? Everything wants to go down to the lowest level, the place where everything is. So there's a stable point right here at B. You can't get out of this little hole. You see it's a little round hole over here. That's where it's stable. It's unstable at C. If you're a little bit to the left of C, it'll come down to this hole at B. If you're a little bit to the right of C, it'll just keep on flowing down. Anything far to the left, if you put a negatively charged ball there, it'll try to get to B. So this is your stable equilibrium. This is what's called an unstable equilibrium. That means as long as if you put something right there and nothing ever blows on it, nothing ever touches it, nothing looks at it wrong, it'll stay there. But as soon as somebody looks at the ball sitting at that point wrong, it's going to fall off. It's like here you're trying to balance a basketball on the top of your finger. Here you're trying to balance a basketball between your feet. Okay, so that's what's going on with that. So this is where you want everything to be, and I'm selecting things again, which is what I don't want to do. So B is correct. If you said B, you were correct. That's what we were looking for on this particular question. So why don't you think about that? Make sure you understand why you got it wrong if you got it wrong. If you got it right, make sure you understand why you got it right. Make sure that you got it right for the right reasons. And after that, you'll be ready for the next part, which is going to be me working some other problems. So it'll be a fun problem. I love these problems. They're a lot of fun for me. And if they're a lot of fun for me, they got to be a lot of fun for you too, right? I mean, that's the way these things work. See you around.